All right. So like I said, we're not going to do the back of that page, so we're skipping to the new thing. This is going to be equilibrium and reversible reactions. So we'll start with reversible reactions. All right. So these are reactions that don't use up all the reactants. So what you end up with is some reactants left over and some product mixed together. So let me give you a reaction, and then I'll explain that more. I'm going to write a chemical reaction, and I'm going to put heat on one side of the reaction. Now, we don't usually put heat because it's not a thing, right? Heat is not matter, it's energy. But we can write heat on one side to indicate what heat does to the reactants and products. So I'm going to put it in the reaction, but don't be confused. It's not stuff, but it's helpful to put it in there. All right, so calcium carbonate. Who has my window open? No, thank you. Okay, so this is a reversible reaction. So this arrow points both ways. So first of all, well, I'll wait till you guys ready.
Yeah.
Sorry. CO3.
Is that heat or just like some like
That's heat.
element?
It's not an element, it's heat. All right, so what this is, we have calcium carbonate. We have calcium carbonate, and it breaks down into calcium oxide and CO2. So it breaks into two pieces. One piece is the carbon and two of the oxygens, and the calcium and the other oxygen stick to each other. All right. So in this reaction, all of this stuff doesn't break down into these two. If it did, we would write it like this. It would look like that. But what this other arrow indicates is that some of this stuff stays around. So we end up with some of this mixed with some of these two at the same time. And if we heat it, right, then that makes the reaction, well, actually, it makes the reaction, more of this stuff get made. But I'm going to get into that. I shouldn't say that yet.
The heat goes just for
It just goes on the left side. I'm going to explain more about why the heat's there in a second, so let me come back to that. All right, let's define equilibrium first. Okay, so when the amount of reactants and products stops changing. Now, what I could have wrote here was when the reaction stops, but that's not entirely correct. So what we're looking at here is, let's say we start out with 100% calcium carbonate and none of this stuff, and we put it into a jar. What happens is some of these particles start breaking down into calcium oxide and CO2 gas. I'm going to put a little G here because it's a gas. And then eventually we build up a lot of these two things, and then some of these start going backwards. In other words, some CO2 particles start banging into calcium oxide particles and recombining to make this stuff again. And so now it's going back and forth, right? And maybe at one point in time, more of these are breaking down into these two particles, and less of these are combining to make calcium carbonate. But then we reach a point where there's enough of each one where the amount of this being produced and the amount of this being produced is equal. And so the amounts stop changing. And you know, there's a set amount based on the temperature, the pressure, and what the particular reaction is. So at one certain situation, we may have it where it's 60% this stuff and 40% this stuff, and that's at equilibrium. So the amounts being produced of each side are the same, and so it's staying the same. And at some other point, if you raise the temperature, maybe now we only got 20% calcium carbonate and 80% calcium oxide and CO2. And that's the new equilibrium at that temperature. So equilibrium means the amounts of each side just stop changing. The same amount of these are combining to make calcium carbonate as the amount of these that are breaking down to make calcium oxide and CO2. Let me give you a slightly different explanation of that, of equilibrium. Let's imagine a situation where we have a town, like let's say, I don't know, Hoboken or Newark or something, right? And there's a whole bunch of people there. Let's say New York City was empty, right? So there's only people on one side of the river and nobody on the other side of the river. And there's a bridge there. Well, some people are going to cross the bridge in New York, right? So we're going to have people going from New Jersey to New York and nobody coming back because New York's empty at the moment. And so New York will start filling up, and so it's going one direction. But eventually you fill up where there's enough people in New York that some people start going back the other way, right? Some people are going across the bridge back into New Jersey. And eventually when we have enough people on both sides, we'll have about the same amount of people going each direction. So the amount of people on both sides stays the same. That's equilibrium. And it doesn't have to be exactly half on each side. It could be maybe most people want to be on one side, so equilibrium is where 80% of people are on one side, 20% on the other side, or whatever it is. But it's where the amounts are staying the same on both sides. Same thing here. The amounts are not changing.
So it's like a scale balance?
It's like a balance, but the balance doesn't have to be equal. It could be the balance where one side gets more, but it's staying the same. All right. One more definition here. And this is funny French word. I don't know how to say it. It doesn't matter. It's a French guy's name. All right. Who knows how to say French words with a French accent? Nobody? All right. Doesn't matter. It's La Chatelier or something. Who cares? Anyway, this guy came up with this idea. If a change is made to a system in equilibrium, what's up?
Did you hear that? No, it was a bird.
Maybe some people doing that stupid video outside.
No. Oh,
Not the bird.
I mean, the water that's in on the
No.
Yeah, turn it off.
wait, where's their bird?
Sounds like it's in the vent.
Anyway,
Person outside.
if a system in equilibrium is in equilibrium, there's a change made. The system will shift back to equilibrium. The
Oh
system
my god.
will shift to get back to equilibrium. There's a bird somewhere.
Hey, where is it?
Sounds like it's in the
All right, so what this means, if you imagine my scenario again with the people on the two sides of the river, if you drop a whole bunch more people on one side, now you just threw off the equilibrium because it's unbalanced on that side. And so more people are going to start going to the other side, start going across the bridge in that one direction until you get back to your balance again. Do the same thing with this reaction. Let's say I had in a jar like 60 grams of this stuff and 20 grams of this stuff, and they're in equilibrium, and then I drop a whole other pound of this stuff into there. Well, more of this is going to break down into calcium oxide and carbon dioxide, and there's going to be less of this being produced. So it's going to get back to some sort of equilibrium where it's balanced, whatever that equilibrium is. Whether it's 90% this and 10% that, or half and half, whatever the particular equilibrium is for that reaction. That makes sense? Okay. All right. Now, what I'm going to do is 3 factors that can change equilibrium. 3 factors that affect equilibrium. What's the first one? What's the one thing that affects everything in chemistry?
Temperature.
Temperature, absolutely. You change the temperature, you change the equilibrium. What's another one? What did Robert Boyle study?
Mold. No, just kidding. That wasn't him, right?
That would be Avogadro and some other people. Nope. Huh? That's going to be the third one, actually. The one I was looking for is pressure. And then finally, 3 will be, it's the amount of each substance, and the amount of this, this, and this. We're going to say concentration. That's more precise. All right. Did everybody get the middle part so far? Can I erase the middle?
Yes.
All right, good. So I'm going to erase everything but the equation here. And then I want you guys to rewrite this equation at the bottom where we're working at. And we'll talk about that one. And I want to add a few more things into this.
Yeah, I made your board.
Yeah, I was about to say, you doing your board.
Really?
'Cause I can still read all of this.
That's okay. I'll just write in the same spots next time. So we got this here, this little G. What's this tell us?
Oh, that's a G? I thought that was a 9.
It tells us that CO2 is a gas. And I'm going to put little S's here because this is a solid and this is a solid. Okay? All right, and heat obviously is not matter, it's energy. All right, so let's talk about how changing these 3 things will affect this particular system. And when I say system, what's up? Oh, okay. So a system is basically wherever this reaction is happening. So we got a jar, and it's got this stuff, it's got this stuff, and it's got this gas in it. That's our system. And we're going to make changes to that system and see how it affects it. So we'll do temperature first. So we'll do like temperature. Okay, so there's 2 possibilities. We could heat it up or we could cool it down. So let's say we heat it, meaning we raise the temperature, right? Anyway, if we heat it up, what's going to happen? So if we heat it, it's kind of the same as saying we're adding something that's on this side of the equation. So since we see heat here, whatever side you're adding something to, the system shifts to the other side. So if we add heat, what's going to happen is more of this is going to break down, and more of these 2 things are going to be produced. The system's going to produce more calcium oxide and more carbon dioxide. And this kind of makes sense because this bigger thing, if you heat it up, the particles start moving around faster, and more of these are going to break apart into 2 smaller particles, and less of these are going to be able to recombine. So if we heat it, we're going to say it shifts to the right. But that's just like shorthand for saying more calcium oxide and more CO2 are produced. So for the rest of this lesson, I'll say shifts right or shifts left. But understand that when I say shifts right, it means make this stuff. When I say shifts left, it means make that stuff. All right, B, our other choice here is we cool it down. So it's like we take our jar with our stuff in it and we stick it in the refrigerator, right? And when you cool something down, heat's coming out of it, right? So it's kind of like we're taking away something on this side of the equation. So when we take heat out of the system, more of these things are going to combine to make more stuff on this side of the equation. So heat's going to be given off and calcium carbonate is going to be produced. It's going to shift to the left. So shift left. And this means CaCO3, calcium carbonate,
I put less.
is made. Did I spell it
Right
wrong?
with S.
And heat is given off. Given off. And this one kind of makes sense too, because as you cool it down, it means the particles slow down. So more of these can combine into this smaller one, single compound instead of 2 separate things. So more of these recombine to make calcium carbonate, and heat is given off from the system. That's what shift to the left means.
What does G mean?
G means it's a gas. This is going to be important in about 2 minutes.
Oh, and those S's are solids?
S's are solids.
I thought those were 5s.
All right, next one we're going to do is pressure and how that affects it. I should hole in here. I should do it. All right. So first we'll do raising the pressure. We'll do raising the pressure yet. So A, raising the pressure, raise pressure. So remember, raising the pressure is like you're taking a system and you're squeezing it smaller, especially the gases. You're compressing them into a smaller space. And if you compress things into a smaller space, just like you're squeezing them together, it would make these two things want to be closer to each other and more likely to combine into this thing, right? But as a more general rule, and this is the one you got to remember, when you raise the pressure, whatever side has gas, it shifts away from that side because the gases are what's being compressed back in with the solid. They're being smashed back into it. So it goes away from the gas and shifts left. Again, remember both these things, all this stuff in here is in the same system. It's just these are coming together and making this stuff. So shifts left means we're making more calcium carbonate, and obviously the system's going to heat up too because it's giving off heat. And because when you raise pressure, things get hot anyway. All right, if we lower the pressure, I'll draw my line there, lower pressure. Well, what's going to happen here?
Shift to the right.
It'll shift to the right. It has to do the opposite. So if you lower the pressure, this is going to be able to expand and give off more gas. It's going to break down and give off more CO2 gas. So that's going to be shift to the right. Yeah, so shifts right. So if we assume we had 50% this stuff and 50% this stuff, then we lower the pressure. Now all of a sudden we got 75% this stuff and only 25% this stuff. More of this broke down into these things. And I only keep repeating that because students sometimes get confused and think this is being made somewhere else, but this is being made from this stuff. And then when it goes the other way, this is being made from that stuff. And it's just they're either combining or breaking apart. All right, so that's it for pressure. Last one is going to be concentration. So again, the idea that if we add something on one side of the equation, then the equation shifts the other direction. So A would be we add calcium carbonate, then what's going to happen?
Left.
Well, calcium carbonate's on the left, so it's got to shift the other way. So it shifts right. And what that means is more of the calcium carbonate has to break down now because we put too much in there. So it shifts right. Just like my example with the bridge, if you throw a whole bunch of people on one side, more people are going to be heading to the other side because there's more people on that side to leave that side, right? So same kind of thing. You put a whole bunch in here, a whole bunch of it's going to start breaking down and making calcium oxide and carbon dioxide. And then this way, if we add, and it doesn't matter which one, let's say we add calcium oxide, that's going to shift left. And remember, even if you just add one, it'll start reacting with the other one and making this stuff. So if I added enough of this stuff, I would use up most of the CO2 and make a bunch of calcium carbonate. Although there would be a limit to that, right? All right, questions? You good?
Are we doing problems or you doing this?
Just questions like this. I'm going to give you an equation. I'm going to say, what if you raise the pressure, lower the pressure, raise temperature, lower temperature, or add one of the reactants or products?
Like
60.
tomorrow, are we gonna be using things?
More of this stuff, yeah. And then Monday we'll have a practice test, and Tuesday we'll have a test. And then we go on to acids and bases. Can you stop that phone, please? All right, so.